Okay, so we're going to pick up on part 2 of this now, where we're going to continue finishing up this little process that we started on the last one. If you remember what we were doing at the very end there, we were talking about this being a Riemann sum, and we had this listed out, and we talked about how, well, yeah, we have 1/2 and 1 and 1.5 and 2 and on down the line, but those aren't actually the values that we need to use for the heights. Those are the x values that give us the heights. And that was kind of done intentionally just to kind of point out the fact that this is really what we need, this information right here, the FO. So then we found this values. Now I kind of cheated a little bit. What I did is I went to my calculator and I went to y equals, and I actually typed in my equation into y equals there, and then I graphed it just to make sure it was actually the shape that I thought it should be. And then I went to table set, which is second window, and I switched to put my table start at 0 and the table step to 1/2, because that was the width of my individual pieces, and I have my independent value on auto there. And then I went to second graph, which takes me to my table, and then ignore this y0 business here, pretend it's not there. And we have these values right here. Well, what do these values mean? Well, these are the individual heights, right? So f of 1/2 is 1.75, f of 1 is 3, and on down the line. And it is a parabola, so it is symmetrical, like we would expect it to be. I add those values together, and I get 21. Half of 21 is 11.5, and this is the area, 11.5 units squared, because it is an area that we just found. Now this might actually mean in terms of our actual problem, maybe this is measuring distance, maybe it's measuring people, maybe it's measuring gallons. This could be all sorts of things, but I'm saying units squared as a representation for this piece right here being area. Okay, but that area might be all sorts of other things. Now I also did talk about the fact that we're going to kind of create the generic version of this. And that kind of takes us back to the drawing for a second first. Notice that all these rectangles touch on the right-hand side. That means that what we actually did here was we found the right hand Riemann sum. Okay? That's what we actually found there, was the right hand Riemann sum. That's what this is. Generically, what we're actually saying that we're doing here is what we did was we did f of the start value, which was a, plus the width, which we did b minus a over the number of intervals. Now if you remember, like, where all does that come from? Think about our widths. What do we do with our widths? That was our end of our interval, that was the beginning of the interval, and that was how many intervals, subintervals we were creating, right? So b minus a over n times which rectangle we're on, right? So we're going to actually call that k, and that's our variable right there. Okay, the k is our variable. And that's how we'd find those. Now, the thing is, all these other pieces here, a, b, and n, are constants. They'd be a set value of some sort, and they wouldn't change. K would change, and that's how we got the different values up here. How we got 1/2 and 1 and on down the line. That's how we got those. But we don't have any way to necessarily count K here and control it, which is why we introduce the idea of summations, which is symbolized with the Greek symbol sigma. We're going to start K at 1, and it's going to go up to whatever value of n that we have designated n to be, which is, in this case, would have been, on the example we did here, was 8. So it would have been 8 here and an 8 there. And that right there times b minus a over n, remember? Okay, now once again, what I'm pointing out here, what we're doing here, this is the width, right? And this right here are the lengths, plural, or the heights, however you want to talk about it. Okay, one width times all those lengths added together, and that gives us the area under the curve. Maybe more particular to say the area between the curves, or the area between the curve and the x-axis, however we want to state that. But that's what we just did there. And this particular one is right-hand Riemann sums. Now, some of you are saying, well, if there's right-hand Riemann sums, does that mean there's left-hand? Yes, there is. Left-hand Riemann sums is the exact same thing. B minus A over N. There's our width. We're still doing the summation from N equal 1 to N. We're still doing the function. We're still starting at A. We're still stepping over by the widths. But in this instance, and this is a piece that you kind of have to conceptualize a little bit here, is think about what we're doing in that case. Instead of starting right here where we're going one width over, we would want to start here at 0. So instead of this being a 1, what would that be? Well, if we're starting here, that first rectangle has no height to it whatsoever. The next one would actually start there, and there's the second rectangle, there's the third rectangle. So it's actually one backwards, so it'd be 0, 1, and 2 instead of 1, 2, and 3. It's just one, it's offset by one step to the left, which means we can accommodate that by doing k minus 1. Now, I will tell you that people run into problems with like k minus 1 versus k, and they spend a lot of time on that. Stop, rewind, rework this out a few times, draw this out a few times. Redraw this shape right here. This is me telling you, redraw this shape right here. And I'm not doing it because if you go through the process and really do this and draw this out for yourself, it'll make a huge difference in your understanding instead of watching me do it. So do it yourself. And this is the left-hand Riemann sum. Once again, it is the area between the curves. This is the right-hand Riemann sum. Okay? And I'll work out a few more examples and post those as well. Enjoy.